Hi everyone. Today we're going to do lesson 7.2 on independent events and conditional probability. First we have a warm-up that is more of a review of what we learned in lesson 7.1. So here we've got 30 AA batteries that are tested to determine how long they're going to last. The results to the nearest minute are recorded here in this list. We want to create a chart that gives the frequency and then the relative frequency of the battery life from this data set of 30 AA batteries. So I've provided you with a chart here for you to fill out. So what we have is we're going to first test and see how many of them have a battery life of 360 to 369 minutes. You'll put the frequency, so how many here, and then the relative frequency, and then we'll express that relative frequency as a percent in this third area. So why don't you pause the video and take a few minutes. And so it's all on the same screen. I can even do this for you if you're watching. That way you can see all of it. And go ahead and fill out the chart. And when you're done, unpause the video and you can come back and check your answers. Welcome back. So what I've done is I've gone through and I've calculated the frequencies that I have. And if all is added up right, I should add up all these frequencies and they should sum to be 30 since there were 30 AA batteries in my test. So when I add 2 plus 3, that's 5, plus 5 is 10, plus 7 is 17, 17 plus 5 is 22, plus the 4 is 26, and then I have 26 plus 3 and 1, which is 4, which makes 30. So it looks like I'm all set and all of my batteries up here have been accounted for. There were 30 total. And so make sure if you don't have those numbers that you go back and take a look and see where you may have had an error. Pause the video to do that. If all of your numbers are good, let's continue with the relative frequencies. So recall from lesson 7.1 to calculate the relative frequency, I'm going to take the frequency and I'm going to divide by the total number of trials. And here the number of trials is 30, the number of batteries I tested. So I'll take 2 divided by the 30, and the relative frequency I'll get is 0.0667. And so then my percent frequency, I don't have a ton of room, is going to be 6.67%. For the next one, when I take 3 out of 30, I get 1/10 or 0.1. So that would be 10% when I think of it as a percent. The next one, I get 5 out of 30 or 1/6, which is 0.167 or 16.7%. So 16.7% of the batteries in my set have a battery life of 380 to 389 minutes. The next one, I do 7 out of 30, and not 300. One too many zeros. And when I do that, I get about 0.233 or 23.3%. The next one is 5 out of 30, so again, I get 0.167, so 16.7%. The next one is 4 out of 30 or 2 out of 15. And there I get 0.133 or 13.3%. The next one, 3 out of 30 again, so 0.1, 10%. And then 1 out of 30 here. When I put that in my calculator, I get 0.033 or 3.3%. So when I'm thinking about relative frequencies, let's remember that when I add up all the relative frequencies here, they should sum to 1. If I'm adding up all of the percents, they should sum to 100%. Since 1 as a relative frequency is 100%, and then remember that the frequency should sum to the total number of trials in your experiment. So that's just a little review to get us going before we get into independent events and dependent events and conditional probability for today. All right, so let's look at this example. It says a standard die is rolled 2 times. I want to find the probability that the sum of any 2 rolls will be greater than or equal to 7. First, notice I'm asking you to calculate a probability. And remember, probability is what we use when we refer to events that are going to happen in the future, potentially. So this is an event. I can't run a simulation. I guess I can run a simulation for it, but it's not like I've already run an event. So this is theoretical. So if I'm going to sum a die 2 times, so the first roll, if I roll it 1 time, there are 6 different outcomes. And then if I roll it a second time, there will be 6 different outcomes potentially, a 1 through a 6. So that means if I take a die and roll it 2 times, there are 36 total possible outcomes. And I'm just using the fundamental counting principle to get 6 times 6, which is 36 possible outcomes. If I want to find the number of times, or what the probability is that the sum is going to be greater than or equal to 7, I think it's going to be best to list the outcomes. I can do that with maybe a tree diagram or a chart, and I think I'm leaning towards a chart for this one. Let's make a chart. And let's let this axis here be roll 1, just spelled roll wrong, R-O-L-L. And then let's let this axis be roll 2. So my outcomes are a 1, a 2, a 3, a 4, a 5, or a 6. And here I get a 1, a 2, a 3, a 4, a 5, or a 6. So like here, I would have a 1, 1. That would represent rolling a 1, then a 1. Here, I would have a 1, then a 2. A 1, then a 3. A 1, then a 4. A 1, then a 5. A 1, then a 6. The next row would mean I rolled a 2, then a 1. Or a 2, then a 2. So this is going to take me a minute or so, and I think it's going to get tedious to sit here and watch me do it because I really want to keep my colors going where the black represents the first roll and the red represents the second roll. So what I am going to do is I'm going to pause the video and fill in this chart, and then I'll come back, and you can pause the video now too and fill out the chart, and then we'll all come back at the same time. All right, so here we are back with our chart all filled out. And so here you can see all 36 outcomes. So if I were to look at this right here, this would mean the first roll was a 2 and the second roll was a 5. So what I'm looking at is all of the outcomes where the sum is greater than or equal to 7. So if I'm just looking at here, I can see along this diagonal, all of the sums are 7 whenever I add up the two numbers. And then I know everything that's kind of to the left and above it, the sums are less than, and all of these to the bottom to the right, they are greater than. So if I'm wondering what the probability is, all I need to do is find out how many times it happens. So I need to count these up. So I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 out of 36, or 7 out of 12, if I want to simplify. And that would be the probability that the sum of the two dice rolls is going to be greater than or equal to 7. You could also think of it this way, kind of like draw my ladder here. I could count up the times it doesn't happen and then subtract that. So if I was going to think of what's called the complement of this event, so the probability that the sum is just strictly less than 7, that would be all the ones that are left over. And instead of counting, I can just take the total number of outcomes, subtract the 21, so that way I know what's left. So that's going to be 15. So at 15 over 36, I can pull a 3 and get 5 out of 12. And notice these complementary events, which we're going to talk about later on in more detail. They're kind of like opposites. They're not exactly opposites, but you can think of it as like opposites, whereas they don't have any outcomes that intersect. We're going to talk about that in section 7.3. So these two events cannot happen at the same time. They're mutually exclusive. And whenever I look at their probabilities, notice that 7/12 and 5/12, if I add these up, I get 12/12 or 1. Whenever I add them up, you get all of the outcomes. But back to the original outcome, I'm getting off on a little bit of a tangent. If I want to find the probability that the sum of any two rolls is greater than or equal to 7, I've got my chart here. I got all 36 outcomes, and I got 7/12, or 21 times out of 36 times, which simplified to be 7/12. Let's see, what says, what would the opposite of the event? Oh, so I got ahead of myself here, and I answered this question right up here. So go ahead and put your notes, all the things we talked about here, just put those notes right here if you're following along with the guided notes. All right, let's look at my next example. Let's look at notation just for a minute, just to review. So if we're talking about particular events, E and F, rather than write out phrases, the relative frequency of E is 50% or the probability of F is 5.7%, we are going to start using more formal notation throughout. So if I'm using relative frequency of E, I will put RF for relative frequency of E equals 0.5. So that's this translation. The probability of F is 5.7%. I'll write P of F is 0.057. Just remember, relative frequencies and probabilities are all numbers between 0 and 1, inclusive. You can have the 0 and the 1. What we want to really talk about today, now that we have relative frequency and probability under our belt, is considering more than one event. So rarely do we measure relative frequency or probability in isolation. More often, we're concerned with the likelihood with a sequence of events or several events that are happening at the same time, or if one event is going to affect another event happening. It's common in these situations to use a single letter to represent an event instead of writing out the situation. Just think about my notation here. If E is some event, F is going to represent some event. It's a lot easier to write one letter instead of defining it every single time. So let's take a look at independent events first. So when an outcome of one event does not affect the outcome of another, we call those independent events. So let's let S represent the event of a snow day happening, and let's let D represent the last digit of your phone number. So does event S affect D? So does the event of a snow day being called at school affect the last digit of the phone number that you have or that maybe you've been given? And I don't think so. I don't think that a snow day happening is going to affect the last digit of your phone number. Now consider, does event D affect S? Does the last digit of your phone number affect whether it's going to be a snow day? I really don't think so. Therefore, we would call events S and D independent events. Independent events. So in class, we talked about coming up with some of our own. We got in groups and we discussed some other independent events. There's one I can recall off the top of my head that I thought was really good. And they said event A is going to be rolling a die, just a fair 6-sided die. So you roll a die, and then B, you're going to take a quarter and you're going to flip a quarter. And we say these you guys told me these were independent events because your dice roll does not affect the outcome of what you're going to get when you flip that quarter and get a head or a tail. So here your outcomes are 1 through 6. And here your outcomes are, a head or a tail. And they just don't affect one another at all. So those are independent events. Now, when the outcome of one event does affect the outcome of another, we call those dependent events. So here I have, let H represent the number of hours you study for a test, and G represents the grade that you get on that test. So I asked, does H affect G? Does the number of hours you study for a test affect the grade that you got on the test? And a lot of people said, yeah, I think so, or at least I like to think so, that if I study more, I'll get a higher grade. Then does G affect H? Does the grade you got on the test affect the number of hours you studied for the test? Does it go in that direction? And we kind of had mixed results. We kind of said maybe, sure, a little hesitant on this one about it going in the direction. But the idea is it really doesn't have to go both ways. It can just be one way or the other. And we didn't really say anything about it having a large effect or a small effect. We said if there's any effect at all, we're going to say these are dependent events. So since we were really confident on does H affect G, we were really confident with this yes right here, we're going to say S and D are dependent events. So now what I want you to do, since I gave you the example from class, from this one right off the cuff, why don't you pause the video and try and think of some events that are dependent, and then once you jot a few down, then we'll move on. Okay, so hopefully you didn't have too much trouble coming up with some dependent events. Some of the one that I thought were really good from class, we had, the first one was stealing a car, and B, going to jail. I think those are safely dependent events. Let's see. The next one that I thought was good was driving a car, and D was getting into a car accident. So I think those are dependent events. Both of these happen to be very negative, but those are the ones I'm recalling from class. All right, so let's take a look at the next slide. So remember that the effect that dependent events have on one another can be large or small. When two events are dependent, all we know is that they have some effect on one another, whether or not we can actually quantify it. So we did this exercise in class. Can we come up with some dependent events that have a large effect on each other and a small effect on each other? I'll let you guys have some time to think about that. You can just pause the video, and then if you want to chat about with me when we get back in class, that would be fun to do. What we want to do next is classify events as independent or dependent. So the first one, selecting a king from a standard deck, not replacing it, and then selecting a queen from the deck. Are these independent or dependent events? And so we are in class together. We said that these are going to be dependent. And the reason it's dependent is because we didn't replace it. If we had replaced it, well, then they'd be independent. But since we didn't, there's going to be less cards that I'm pulling from on the second one, and so that's going to make the outcome change a little bit. 2 says tossing a coin and getting ahead, and then rolling a 6-sided die and obtaining a 6. And that is going to be independent, because the coin flip is not going to affect the dice roll. 3, driving over 85 miles per hour and then getting into a car accident. And you guys said that these were independent or dependent. Let's see. You guys said these were dependent events, that driving over 85 miles an hour and getting in a car accident. You guys said that this is probably falling under the smaller side of dependency, because you don't really know, but you still think that they are dependent. Okay, next we're going to talk about conditional, relative frequency, or probability. When considering events in a sequence, the outcome of one may be related to the outcome of another. For example, let's consider the event of getting lung cancer and the event of smoking or being a smoker. If you're a smoker, it significantly changes the probability that you will develop lung cancer. I think we can all agree that these are going to be dependent events. We would call the probability that you develop lung cancer, given that you are a smoker, a conditional probability. And the notation is going to be with this bar. So it's probability that you develop lung cancer, given that you are a smoker, is how that would read. And the order is going to matter. If I write this the other way, the probability of S given L, this would be the probability that you're a smoker given that you've developed lung cancer. So it would be the probability, my goodness, I just hit something and now I've lost my way. There we go. probability of S given L. So the order is going to matter. So what I have here is I have some data. It's a partial table from the Three Stooges, an illustrated history by Michael Fleming from this article. And what we have here is you can see this two-way chart. We've got 187 total Three Stooges videos that were observed. Here we see that in 20 of them, Curly had 0 to 5 slaps. Shemp had 0 to 5 slaps 9 times. Joe had it 5 times, making 34 out of the 187 where there were 0 to 5 slaps going on. So, from each of those folks. So let's calculate the relative frequency that Curly did the slapping, given that there were 26 to 30 slaps. So right here, when I'm looking at this given that, I'm not looking at the whole subset of 187. I'm only looking at this row that represents 26 to 30 slaps. And there I can see that I'm only looking at 11 total. So out of those 11, what's the relative frequency that Curly did the slapping? Well, I look here and see it's 4 out of the 11. So that would be a relative frequency that Curly did the slapping, given that there were 26 to 30 slaps in the movie. That's a conditional probability. Let's look at the next one. Let me change colors here. So here it says, what is the relative frequency that Shemp did the slapping, given that there were 11 to 15 slaps? So if I look at that row, 11 to 15 slaps, that's only 37 out of the total subset. So notice this is kind of what's telling me my denominator here, like what the subset I'm looking at. What is the relative frequency that Shemp did the slapping? Looks like 16 out of the 37. I always like to do one more thing to distinguish the difference between an AND statement, which we're going to push even further into in 7.3 and foreshadow a little bit. If I ask the relative frequency that Curly did the slapping and there were 26 to 30 slaps, now I'm looking at all 187. So that Curly did the slapping and there were 26 to 30 slaps. I'm looking at all of them, and then I got to find the intersection where these two things are happening. So I'm looking at the 4 here where Curly did the slapping and there were 26 to 30. That would be the 4 out of the 187. So notice the difference between the conditional statement in number 1 and this AND statement in number 3. So it's really a difference between what is the subset you're looking at if it's conditional versus the total when it's not a conditional statement. My denominator. All right, so let's talk about a formal definition of independent events. So events A and E are considered to be independent if and only if the probability of A given B is equal to the probability of A, and the probability of B given A is equal to the probability of B. And this works for relative frequency too. What this is saying here is that when I calculate the probability of A given B, and I just get the same thing as the probability of A, this means B did not affect A. And here, if I calculate the probability of B given A, and it's equal to the probability of B, well, this means that A did not affect B. So when I have both of these things happening at the same time, and I do have to prove both of them, then this means that A is not affecting B, B is not affecting A, and therefore they are independent events. Let's look at this one example. A fair 6-sided die is rolled, and then a fair 2-sided coin is tossed. What is the probability that the result of the dice roll is even and a tail is flipped? I think it would be best to go ahead and do a chart method. So first I have the dice roll. So if I'm looking at, I don't want to do it. That's 6 events. I didn't leave myself a lot of room here, did I? I'm just going to make a chart. So when I roll a die, I can get a 1, a 2, a 3, a 4, a 5, or a 6. And when I flip, I can get a head or a tail. So let's do all of these outcomes first. And then I could also get a tail. So I need another row for that. So I've got 12 total outcomes that are pretty easy to list. So I want to know what the probability is that a dice roll is even. So I'm looking at all the even dice rolls here. And a tail is flipped. So then when I even make that smaller, I can see there's only 3 times out of the 12, or 1/4, or 0.25, there's a 25% chance that's going to happen, that I get an even roll and a tail is flipped. Let's look at the next example. It says a fair 6-sided die is rolled, and then we've got the coin being tossed to get a head or a tail. So the same outcomes here that I have, my 12 outcomes. I know what's the probability that a tail is flipped given that the result of the dice roll was even. Now, so that's going to be worded a little differently. This is a conditional probability. So I'm going to rewrite these results just because I wrote too much on my other ones. So I'll have a 1, 1, 2, 2, 3, 3, 4, 4, and so forth. And then I'll have head, tail. Okay. So it says the result that the tail flipped was that a tail was flipped given that the result of the dice roll is even. So first, I'm not looking at all the results. I'm looking at an even dice roll only. So I am no longer even considering these as options, meaning that I'm only looking at these 6 outcomes now. Now, if I have a tail being flipped, I still have the original 3 that I have in the last example, but now it's 3 out of 6, or 1/2, or 0.5 or 50% chance for this conditional probability. Notice that it changes my denominator from the total outcomes to only the one where the result of the dice roll was even. All right, so in the next example, 2 cards are selected in sequence from a standard deck. Find the probability that the second card is a queen, given that the first card is a king. We are going to assume that the first card is not replaced. So here, let's take a look at the first one. Let's find the probability, when I pick the first card, that I get that, let's see, king, given that it's a king. Well, that would be 4 out of 52, correct? Now I want to find the probability that the second card is a queen, given that the first card was a king. So it's not really necessary that I know this, other than it's good to know that I have 4 kings. But what's important is that I'm assuming here that the first card that I picked was a king. So that means when I'm going to pick the second card, I no longer have 52 cards anymore. I only have 51, because remember, I've got a king already. And now I need to find, well, what's the probability out of those 51 that I get a queen? Well, I know I still have 4 queens left in the deck. So the probability that I get a queen, given that the first one was a king, is 4 out of 51. Think about if I adjust this just a little bit. I'm going to change the problem. Let's find the probability that the second card is a queen, given that the first card was a queen. Well, the probability of just getting a queen on the first one is 4 out of 52. It's the same thing as probability of getting a king. Now, if I find the probability of drawing a queen, given that the first one was a queen, not replaced, I've got 51 cards now in my deck, because I already pulled a queen. But now when I'm saying, well, what's the probability that I'm going to pull another queen, it changes this numerator too, because there's only 3 queens left. So that would be 3 out of 51. Again, this is all assuming that the first card is not replaced, because if I replace the first card, these would become independent events if they were going to be replaced. All right, I believe this is going to be my last example here before I cut you loose to work on the problem set. So a study was conducted where researchers examined the IQs of 6-year-olds along with the presence or lack of a presence of a specific gene they were looking at. There's 102 kids that were used in the study, and the table outlines the results. So you can see children who tested for a high IQ or a normal IQ, whether the gene is present or not present. So in the first problem, I want to find the relative frequency that a child has a high IQ given that the child has the gene. So this is conditional probability. So given that the child has the gene means I'm only looking at the 72 here that have the gene. Of those 72, how many of them have a high IQ? That's 33. So I'll have 33 out of 72. B, it says find the relative frequency that a child just does not have the gene. They do not have the gene. So here it's not conditional at all. I'm looking at all 102 participants of the 6-year-olds. And how many of them do not have the gene? I'm looking at the totals here, 30 out of the 102. Now the next one, I want to find the relative frequency that a child does not have the gene given that the child has a normal IQ. So I'm looking at only the kids who have a normal IQ, that subset of 50 are the ones I'm looking at. Out of those 50, what is the relative frequency that the child does not have the gene? And that's right here. It looks like 11 out of 50. So you can see here on A and C, we're looking at conditional probability, and not probability, relative frequency, because this is a data-driven. But it works the same way for probability. When you see that, given that, you're not looking at the total amount anymore. In my survey or in my study, in this case, I'm looking at a subset, whereas B is just a normal problem. All right, so next you guys are all ready to do problem set 7.2. See you guys tomorrow.